In quantum mechanics, perturbation theory is a set of approximation schemes directly related to mathematical perturbation for describing a complicated quantum system in terms of a simpler one. The idea is to start with a simple system for which a mathematical solution is known, and add an additional perturbing Hamiltonian representing a weak disturbance to the system. If the disturbance is not too large, the various physical quantities associated with the perturbed system can be expressed as corrections to those of the simple system. These corrections, being small compared to the size of the quantities themselves, can be calculated using approximate methods such as asymptotic series. The complicated system can therefore be studied based on knowledge of the simpler one. Applications of perturbation theory. Perturbation theory is an important tool for describing real quantum systems, as it turns out to be very difficult to find exact solutions to the Schrödinger equation for Hamiltonians of even moderate complexity. The Hamiltonians to which we know exact solutions, such as the hydrogen atom, the quantum harmonic oscillator and the particle in a box, are too idealized to adequately describe most systems. Using perturbation theory, we can use the known solutions of these simple Hamiltonians to generate solutions for a range of more complicated systems. For example, by adding a perturbative electric potential to the quantum mechanical model of the hydrogen atom, we can calculate the tiny shifts in the spectral lines of hydrogen caused by the presence of an electric field. This is only approximate because the sum of a Coulomb potential with a linear potential is unstable, although the tunneling time is very long. This instability shows up as a broadening of the energy spectrum lines, which perturbation theory fails to reproduce entirely. The expressions produced by perturbation theory are not exact, but they can lead to accurate results as long as the expansion parameter, say I plus or minus, is very small. Typically, the results are expressed in terms of finite power series in I plus or minus that seem to converge to the exact values when summed to higher order. After a certain order n to 1/I plus or minus, however, the results become increasingly worse since the series are usually divergent. There exist ways to convert them into convergent series, which can be evaluated for large expansion parameters, most efficiently by variational method. In the theory of quantum electrodynamics, in which the electron-photon interaction is treated perturbatively, the calculation of the electron's magnetic moment has been found to agree with experiment to 11 decimal places. In QED and other quantum field theories, special calculation techniques known as Feynman diagrams are used to systematically sum the power series terms. Under some circumstances, perturbation theory is an invalid approach to take. This happens when the system we wish to describe cannot be described by a small perturbation imposed on some simple system. In quantum chromodynamics, for instance, the interaction of quarks with the gluon field cannot be treated perturbatively at low energies because the coupling constant becomes too large. Perturbation theory also fails to describe states that are not generated adiabatically from the free model, including bound states and various collective phenomena such as solitons. Imagine, for example, that we have a system of free particles, to which an attractive interaction is introduced. Depending on the form of the interaction, this may create an entirely new set of eigenstates corresponding to groups of particles bound to one another. An example of this phenomenon may be found in conventional superconductivity, in which the phonon-mediated attraction between conduction electrons leads to the formation of correlated electron pairs known as Cooper pairs. When faced with such systems, one usually turns to other approximation schemes, such as the variational method and the WKB approximation. This is because there is no analog of a bound particle in the unperturbed model, and the energy of a soliton typically goes as the inverse of the expansion parameter. However, if we integrate over the solitonic phenomena, the non-perturbative corrections in this case will be tiny. Of the order of exp, a 1 per gram, or exp, a 1 per gram 2, in the perturbation parameter G. Perturbation theory can only detect solutions close to the unperturbed solution, even if there are other solutions for which the perturbative expansion is not valid. The problem of non-perturbative systems has been somewhat alleviated by the advent of modern computers. it has become practical to obtain numerical non-perturbative solutions for certain problems, using methods such as density functional theory. These advances have been of particular benefit to the field of quantum chemistry. Computers have also been used to carry out perturbation theory calculations to extraordinarily high levels of precision, which has proven important in particle physics for generating theoretical results that can be compared with experiment. Time-independent perturbation theory. Time-independent perturbation theory is one of two categories of perturbation theory, the other being time-dependent perturbation. In time-independent perturbation theory, the perturbation Hamiltonian is static. Time-independent perturbation theory was presented by Erwin Schrödinger in a 1926 paper, shortly after he produced his theories in wave mechanics. In this paper, Schrödinger referred to earlier work of Lord Rayleigh, who investigated harmonic vibrations of a string perturbed by small inhomogeneities. This is why this perturbation theory is often referred to as Rayleigh-Schrödinger perturbation theory. First-order corrections equals, we begin with an unperturbed Hamiltonian HO, which is also assumed to have no time dependence. It has known energy levels and eigenstates, arising from the time-independent Schrödinger equation. For simplicity, we have assumed that the energies are discrete. The superscripts denote that these quantities are associated with the unperturbed system. Note the use of Bra-Ket notation. We now introduce a perturbation to the Hamiltonian. Let V be a Hamiltonian representing a weak physical disturbance, such as a potential energy produced by an external field. Let I be a dimensionless parameter that can take on values ranging continuously from 0 to 1. The perturbed Hamiltonian is. The energy levels and eigenstates of the perturbed Hamiltonian are again given by the Schrödinger equation. Our goal is to express n and in terms of the energy levels and eigenstates of the old Hamiltonian. If the perturbation is sufficiently weak, we can write them as power series in I. Where, when I equals 0, these reduce to the unperturbed values, which are the first term in each series. Since the perturbation is weak, the energy levels and eigenstates should not deviate too much from their unperturbed values, and the terms should rapidly become smaller as we go to higher order. Substituting the power series expansion into the Schrödinger equation, we obtain. Expanding this equation and comparing coefficients of each power of I results in an infinite series of simultaneous equations. The zeroth order equation is simply the Schrödinger equation for the unperturbed system. The first order equation is operating through by. The first term on the left-hand side cancels with the first term on the right-hand side. This leads to the first-order energy shift. This is simply the expectation value of a perturbation Hamiltonian while the system is in the unperturbed state. This result can be interpreted in the following way: suppose the perturbation is applied, but we keep the system in the quantum state, which is a valid quantum state though no longer an energy eigenstate. The perturbation causes the average energy of this state to increase by. However, the true energy shift is slightly different, because the perturbed eigenstate is not exactly the same as. These further shifts are given by the second and higher order corrections to the energy. Before we compute the corrections to the energy eigenstate, we need to address the issue of normalization. We may suppose. But perturbation theory assumes we also have. It follows that at first order in I, we must have. Since the overall phase is not determined in quantum mechanics, without loss of generality, we may assume is purely real. Therefore, and we deduce. To obtain the first-order correction to the energy eigenstate, we insert our expression for the first-order energy correction back into the result shown above of equating the first-order coefficients of I. We then make use of the resolution of the identity, where the are in the orthogonal complement of. The result is. For the moment, suppose that the zeroth order energy level is not degenerate, that is there is no eigenstate of HO in the orthogonal complement of the energy. We multiply through by, which gives. And hence the component of the first order correction along since by assumption. In total we get The first-order change in the nth energy eigenkit has a contribution from each of the energy eigenstates Ka per mil n. Each term is proportional to the matrix element, which is a measure of how much the perturbation mixes eigenstate n with eigenstate K. It is also inversely proportional to the energy difference between eigenstates K and n, which means that the perturbation deforms the eigenstate to a greater extent if there are more eigenstates at nearby energies. We see also that the expression is singular if any of these states have the same energy as state n, which is why we assumed that there is no degeneracy. Second order and higher corrections equals, we can find the higher order deviations by a similar procedure, though the calculations become quite tedious with our current formulation. Our normalization prescription gives that up to second order, the expressions for the energies and eigenstates are. Extending the process further, the third order energy correction can be shown to be effects of degeneracy equals, suppose that two or more energy eigenstates are degenerate. The first-order energy shift is not well defined, since there is no unique way to choose a basis of eigenstates for the unperturbed system. The calculation of the change in the eigenstate is problematic as well, because the operator does not have a well-defined inverse. Let D denote the subspace spanned by these degenerate eigenstates. No matter how small the perturbation is, in the degenerate subspace D the energy differences between the eigenstates HO are zero, so complete mixing of at least some of these states is assured. Thus the perturbation cannot be considered small in the D subspace, and in that subspace the new Hamiltonian must be diagonalized first. These correct perturbed eigenstates in D are now the basis for the perturbation expansion. Where only eigenstates outside of the D subspace are considered to be small. For the first-order perturbation we need to solve the perturbed Hamiltonian restricted to the degenerate subspace D. Simultaneously for all the degenerate eigenstates, where are first-order corrections to the degenerate energy levels. This is equivalent to diagonalizing the matrix. This procedure is approximate, since we neglected states outside the D subspace. The splitting of degenerate energies is generally observed. Although the splitting may be small compared to the range of energies found in the system, it is crucial in understanding certain details, such as spectral lines in electron spin resonance experiments. Higher-order corrections due to other eigenstates can be found in the same way as for the non-degenerate case. The operator on the left-hand side is not singular when applied to eigenstates outside D, so we can write. But the effect on the degenerate states is minuscule, proportional to the square of the first-order correction. Near-degenerate states should also be treated in the above manner, since the original Hamiltonian won't be larger than the perturbation in the near-degenerate subspace. An application is found in the nearly free electron model, where near-degeneracy treated properly gives rise to an energy gap even for small perturbations. Other eigenstates will only shift the absolute energy of all near-degenerate states simultaneously. Generalization to multi-parameter case equals, the generalization of the time-independent perturbation theory to the case where there are multiple small parameters in place of I can be formulated more systematically using the language of differential geometry, which basically defines the derivatives of the quantum states and calculate the perturbative corrections by taking derivatives iteratively at the unperturbed point. Hamiltonian and force operator, from the differential geometric point of view, a parameterized Hamiltonian is considered as a function defined on the parameter manifold that maps each particular set of parameters to an Hermitian operator H, I1/4 that acts on the Hilbert space. The parameters here can be external field, interaction strength, or driving parameters in the quantum phase transition. Let n, I1/4 and be the nth eigenenergy and eigenstate of H, I1/4 respectively. In the language of differential geometry, the states form a vector bundle over the parameter manifold, on which derivatives of these states can be defined. The perturbation theory is to answer the following question: given and at an unperturbed reference point, how to estimate the n, I1/4 and at I1/4 close to that reference point. Without loss of generality, the coordinate system can be shifted, such that the reference point is said to be the origin. the following linearly parameterized Hamiltonian is frequently used. If the parameters I1/4 are considered as generalized coordinates, then phi1/4 should be identified as the generalized force operators related to those coordinates. Different indices I1/4 label the different forces along different directions in the parameter manifold. For example, if I1/4 denotes the external magnetic field in the I1/4 direction, then phi1/4 should be the magnetization in the same direction. Perturbation theory is power series expansion. The validity of the perturbation theory lies on the adiabatic assumption, which assumes the eigenenergies and eigenstates of the Hamiltonian are smooth functions of parameters such that their values in the vicinity region can be calculated in power series of the parameters. Here AI1/4 denotes the derivative with respect to I1/4. When applying to the state, it should be understood as the covariant derivative if the vector bundle is equipped with non-vanishing connection. All the terms on the right-hand side of the series are evaluated at I1/4 equals 0, for example n per mil n, 0, and. This convention will be adopted throughout this subsection, that all functions without the parameter dependence explicitly stated are assumed to be evaluated at the origin. The power series may converge slowly or even not converge when the energy levels are close to each other. The adiabatic assumption breaks down when there is energy level degeneracy, and hence the perturbation theory is not applicable in that case. Hellman-Feynman theorems. The above power series expansion can be readily evaluated if there is a systematic approach to calculate the derivatives to any order. Using the chain rule, the derivatives can be broken down to the single derivative on either the energy or the state. The Hellman-Feynman theorems are used to calculate these single derivatives. The first Hellman-Feynman theorem gives the derivative of the energy. The second Hellman-Feynman theorem gives the derivative of the state. For the linearly parameterized Hamiltonian, AI1/4 H simply stands for the generalized force operator phi1/4. The theorems can be simply derived by applying the differential operator AI1/4 to both sides of the Schrödinger equation, which reads. Then overlap with the state from left and make use of the Schrödinger equation again. Given that the eigenstates of the Hamiltonian always form an orthonormal basis, the cases of m equals n and ma per mil n can be discussed separately. The first case will lead to the first theorem and the second case to the second theorem, which can be shown immediately by rearranging the terms. With the differential rules given by the Hellman-Feynman theorems, the perturbative correction to the energies and states can be calculated systematically. Correction of energy and state. To the second order, the energy correction reads. The first-order derivative AI1/4 n is given by the first Hellman-Feynman theorem directly. To obtain the second-order derivative AI1/4 AI1/2 n, simply applying the differential operator AI1/4 to the result of the first-order derivative, which reads. Note that for linearly parameterized Hamiltonian, there is no second derivative AI1/4 AI1/2 equals 0 on the operator level. Resolve the derivative of state by inserting the complete set of bases. Then all parts can be calculated using the Hellman-Feynman theorems. In terms of Lie derivatives, according to the definition of the connection for the vector bundle. Therefore the case m equals n can be excluded from the summation, which avoids the singularity of the energy denominator. The same procedure can be carried on for higher-order derivatives, from which higher-order corrections are obtained. The same computational scheme is applicable for the correction of states. The result to the second order is as follows. Both energy derivatives and state derivatives will be involved in deduction. Whenever a state derivative is encountered, resolve it by inserting the complete set of bases, then the Hellman-Feynman theorem is applicable. Because differentiation can be calculated systematically, the series expansion approach to the perturbative corrections can be coded on computers with symbolic processing software like Mathematica. Effective Hamiltonian, let H, 0, be the Hamiltonian completely restricted either in the low-energy subspace or in the high-energy subspace, such that there is no matrix element in H, 0, connecting the low and the high energy subspaces, that is, if let V1/4 equals AI1/4 H be the coupling terms connecting the subspaces. Then when the high energy degrees of freedoms are integrated out, the effective Hamiltonian in the low energy subspace reads here are restricted in the low energy subspace. The above result can be derived by power series expansion of. In a formal way, it is possible to define an effective Hamiltonian that gives exactly the low-lying energy states and wave functions. In practice, some kind of approximation is generally required. Time-dependent perturbation theory equals method of variation of constants equals time-dependent perturbation theory, developed by Paul Dirac, studies the effect of a time-dependent perturbation V, T, applied to a time-independent Hamiltonian HO. Since the perturbed Hamiltonian is time-dependent, so are its energy levels and eigenstates. Thus, the goals of time-dependent perturbation theory are slightly different from time-independent perturbation theory. One is interested in the following quantities: the time-dependent expectation value of some observable A, for a given initial state. The time-dependent amplitudes of those quantum states that are energy eigenkets in the unperturbed system. The first quantity is important because it gives rise to the classical result of an A measurement performed on a macroscopic number of copies of the perturbed system. For example, we could take A to be the displacement in the x direction of the electron in a hydrogen atom, in which case the expected value, when multiplied by an appropriate coefficient, gives the time-dependent dielectric polarization of a hydrogen gas. With an appropriate choice of perturbation, this allows one to calculate the AC permittivity of the gas. The second quantity looks at the time-dependent probability of occupation for each eigenstate. This is particularly useful in laser physics, where one is interested in the populations of different atomic states in a gas when a time-dependent electric field is applied. These probabilities are also useful for calculating the quantum broadening of spectral lines and particle decay in particle physics and nuclear physics. We will briefly examine the method behind Dirac's formulation of time-dependent perturbation theory. Choose an energy basis for the unperturbed system superscripts for the eigenstates, because it is not useful to speak of energy levels and eigenstates for the perturbed system. If the unperturbed system is in eigenstate at time t equals 0, its state at subsequent times varies only by a phase. Now, introduce a time-dependent perturbing Hamiltonian V, T. The Hamiltonian of the perturbed system is. Let denote the quantum state of the perturbed system at time t. It obeys the time-dependent Schrödinger equation. The quantum state at each instant can be expressed as a linear combination of the complete eigenbasis of whether Cn, T, S are to be determined complex functions of T which we will refer to as amplitudes. We have explicitly extracted the exponential phase factors on the right-hand side. This is only a matter of convention, and may be done without loss of generality. The reason we go to this trouble is that when the system starts in the state and no perturbation is present, the amplitudes have the convenient property that, for all t, Cj, t, equals 1 and Cn, t, equals 0 if Na permel j. The square of the absolute amplitude Cn, t, is the probability that the system is in state n at time t, since plugging into the Schrödinger equation and using the fact that a/at acts by a chain rule, one obtains. By resolving the identity in front of V, this can be reduced to a set of partial differential equations for the amplitudes. The matrix elements of V play a similar role as in time-independent perturbation theory, being proportional to the rate at which amplitudes are shifted between states. Note, however, that the direction of the shift is modified by the exponential phase factor. Over times much longer than the energy difference n, the phase winds around zero several times. If the time dependence of V is sufficiently slow, this may cause the state amplitudes to oscillate. Up to this point, we have made no approximations, so this set of differential equations is exact. By supplying appropriate initial values Cn, T, we could in principle find an exact solution. This is easily done when there are only two energy levels, and this solution is useful for modeling systems like the ammonia molecule. However, exact solutions are difficult to find when there are many energy levels, and one instead looks for perturbative solutions. These may be obtained by expressing the equations in an integral form. Repeatedly substituting this expression for Cn back into right-hand side, yields an iterative solution. Where, for example, the first-order term is. Several further results follow from this, such as Fermi's golden rule, which relates the rate of transitions between quantum states to the density of states at particular energies. Or the Dyson series, obtained by applying the iterative method to the time evolution operator, which is one of the starting points for the method of Feynman diagrams. Method of Dyson series time-dependent perturbations can be reorganized through the technique of the Dyson series. The Schrödinger equation has the formal solution, where T is the time ordering operator. Thus, the exponential represents the following Dyson series. Consider the following perturbation problem. Assuming that the parameter I is small and that the problem has been solved. Perform the following unitary transformation to the interaction picture. Consequently, the Schrödinger equation simplifies to. So it is solved through the above Dyson series. As a perturbation series with small I. Using the solution of the unperturbed problem and, yields, to first order. Thus, the system, initially in the unperturbed state, by dint of a perturbation can go into the state. The corresponding transition probability amplitude to first order is. As detailed in the previous section while the corresponding transition probability to a continuum is furnished by Fermi's golden rule. As an aside, note the time-independent perturbation theory is also organized inside this time-dependent perturbation theory Dyson series. To see this, write the unitary evolution operator, obtained from the above Dyson series, as and take the perturbation V to be time-independent. Using the identity resolution with for a pure discrete spectrum, write. It is evident that, at second order, one must sum on all the intermediate states. Assume the asymptotic limit of larger times. This means that, at each contribution of the perturbation series, one has to add a multiplicative factor and the integrands for I micron arbitrarily small. Thus the limit TAA gives back the final state of the system by eliminating all oscillating terms, but keeping the secular ones. The integrals are thus computable, and, separating the diagonal terms from the others yields. Where the time-secular series yields the eigenvalues of the perturbed problems specified above, recursively. Whereas the remaining time constant part yields the corrections to the stationary eigenfunctions also given above, the unitary evolution operator is applicable to arbitrary eigenstates of the unperturbed problem and, in this case, yields a secular series that holds at small times. Strong perturbation theory. In a similar way as for small perturbations, it is possible to develop a strong perturbation theory. Let us consider as usual the Schrödinger equation. And we consider the question if a dual Dyson series exists that applies in the limit of a perturbation increasingly large. This question can be answered in an affirmative way and the series is the well-known adiabatic series. This approach is quite general and can be shown in the following way. Let us consider the perturbation problem. Being IAA. Our aim is to find a solution in the form. But a direct substitution into the above equation fails to produce useful results. This situation can be adjusted making a rescaling of the time variable as producing the following meaningful equations. That can be solved once we know the solution of the leading order equation. But we know that in this case we can use the adiabatic approximation. When does not depend on time one gets the Werner-Kirkwood series that is often used in statistical mechanics. Indeed, in this case we introduce the unitary transformation. That defines a free picture as we are trying to eliminate the interaction term. Now, in dual way with respect to the small perturbations, we have to solve the Schrödinger equation. And we see that the expansion parameter A appears only into the exponential and so, the corresponding Dyson series, a dual Dyson series, is meaningful at large is and is. After the rescaling in time we can see that this is indeed a series and justifying in this way the name of dual Dyson series. The reason is that we have obtained the series simply interchanging HO and V and we can go from one to another applying this exchange. This is called duality principle in perturbation theory. The choice yields, as already said, a Winner-Kirkwood series that is a gradient expansion. The Winner-Kirkwood series is a semi-classical series with eigenvalues given exactly as for WKB approximation. Examples. Example of first-order perturbation theory. Ground state energy of the quartic oscillator equals, let us consider the quantum harmonic oscillator with the quartic potential perturbation and the Hamiltonian. The ground state of the harmonic oscillator is, and the energy of unperturbed ground state is. Using the first-order correction formula we get or equals example of first and second-order perturbation theory. Quantum pendulum equals, consider the quantum mathematical pendulum with the Hamiltonian. With the potential energy taken as the perturbation that is. The unperturbed normalized quantum wave functions are those of the rigid rotor and are given by and the energies. The first-order energy correction to the rotor due to the potential energy is. Using the formula for the second-order correction one gets or. See also, Fermi's golden rule. References